Hi, in this video we're going to look at how we find out distances between lines and points. To begin with, we're going to look at finding the shortest distance between the origin and a line. The line's given by the vector equation 0, 9, 4 plus mu 5 minus 3 and 2. Let's just imagine what this looks like. Here is that line that we're talking about, and here is the origin. So there's origin. And there's that line R. Now I want you to imagine that somewhere on this line R there is a point, and I'm going to call that point A, and I'm wanting to know the shortest distance to that line. So in other words, it's going to have to be the perpendicular distance from the origin to that point A. Now I can determine the coordinates of that point A by looking at the line. The vector equation of the line tells me that the position vector of A, so in other words OA, is going to be 0 plus 5 mu, so in other words it's just going to be 5 mu, 9 minus 3 mu, and 4 plus 2 mu. So there is my position vector OA. Now, I'm going to call another point in that line B, simply because I can tell you that I also have a direction vector AB, and that's given by the direction vector of the line. That's going to be 5 minus 3 and 2. I don't have to worry about which way it's going because I've got this multiplying factor of mu in front of it. So, these two lines are at right angles to each other. So in other words, I know that OA is perpendicular to AB, and that means that OA dot producted with AB, let's put the lines on the top to indicate that we're dealing with vectors, that has to equal 0. So in other words, I can say 5 mu, 9 minus 3 mu, and 4 plus 2 mu, that dot producted with 5 minus 3 and 2, that has to come up at 0. So now it's just a case of being able to connect these together. So I can say 25 mu minus 27 plus 9 mu, if I multiply that by that, plus multiply this by this, I'm going to get 8 plus 4 mu. That has to come up with a grand total of 0. Tidying all of this up, I'm going to get 38 mu is minus 19 is equal to 0. I think you can see from that situation that mu is going to equal a half. In which case, I can go back to that position vector OA, and that position vector OA, if you remember, was 5 mu, 9 minus 3 mu, and 4 plus 2 mu. And I'm going to substitute in the value of mu being equal to a half. So therefore, I'm going to get that the line OA, the position vector OA, is going to be 5 times a half, in other words, 5 over 2. 9 minus 3 over 2, that's going to be 7.5. And 4 plus 2 mu, that's going to be 4 plus 1, that's going to give me 5. And so there is my position vector OA. That's the actual value of it. Now I didn't want the actual position of it, I wanted to know how far away it was from the origin. So in other words, I'm looking for the magnitude of the vector OA, and then I'm going to use my good old friend Pythagoras, and we're simply going to say it's 5 over 2 squared plus 7.5 squared plus 5 squared. And when we crunch all of that together, and so there we have our final answer. We are 9.35 units away from the origin. That's to 3 significant figures. Now the second situation looks like this. We want to find the shortest distance from a point to a line. So we've got a point P, it's a 0.63 minus 1, and we've got a line whose vector equation is 401, that's a point on the line, and the direction vector of 201. So let's make a little diagram of this. First of all, here's our line. I'm going to have a point over here that I'm going to call the point A, and that's this point over here, the point that we got on the line, 0, 4, and 1. That's some arbitrary point on the line. And I'm going to call this vector AM for argument's sake. And this has a direction vector, so I know that AM is the direction vector 2, 0, and 1. I also have some point P that's over here, beg your pardon, and P has the coordinates of 6, 3, and minus 1. What I'm going to do is I'm going to join up a line between A and P, and I can now work out some displacement vectors. So, what do I know? Well, I know that I've got a displacement vector AM, that is the vector 2, 1, 0, 1. I also have a displacement vector AP, and that's going to be 6 minus 0. That's a 0, not a 6. 6 minus 0. 3 minus 4, and minus 1 minus 1. In other words, we have a displacement vector of 6 minus 1 minus 2. That's the displacement vector AP. Now, AM has a magnitude that I can work out, and that's going to be the square root of 5. And AP has a magnitude that I can work out, and that's going to be the square root of 36 and 4 and 1, square root of 41. So I now have enough information to work out the size of that angle that's going between the vector AP and the vector AM. So I can say that the cos of theta is going to be AP dot AM divided by the magnitude of AP, which is the square root of 41, multiplied by the square root of 5. And if I work out that dot product, it's going to be 6 times 2, which is 12, plus 0 times minus 1, that's 0. And then 1 times minus 2, which is minus 2. So I'm going to have 12 minus 2 up on the top over here. And the bottom I'm going to have root 41 times root 5. So in other words, it's going to be 10 over the square root of 205. And so I can work out the angle of theta. It's going to be cos the minus 1 of 10 over root 205. And when I punch all of that into the calculator, let's see, shift, to clear things, turn it on, shift cos and 10 over square root of 205, close the brackets, no, don't need to close the brackets there, I need to take it out, and that comes up with the angle of theta being 45.7 degrees, approximately, to 1 dp. So having got that, what have I got now? Basically, I have a triangle that looks like this. There's the point A, there's the point P, there's the point M. No, it's not looking like that at all. It's looking like this. That's perpendicular. This is P. I know that this angle over here is 45.7. I know this distance here is the square root of 41. And the shortest distance from the point P to the point M is going to be that distance over here. So if I use some basic trig, I can say MP over the square root of 41 is going to be the sine of 45.7. and just manipulating it around, MP is going to be root 41 times the sine of 45.7. And if I work that out, times the square root of 41, and that comes up to a number 4.58 approximately. That's to 3 significant figures. And so I've worked out the distance of the point P from the line. I could have done this a slightly different way. I show it to you because I like to give you alternates. So we had our line R, which was the line 0, 4, 1 plus lambda times 2, 0, 1. And we had our point P over here that had the coordinates of, 6, 3, and -1. And our shortest distance was going to be this line that was at right angles to it. Now, the coordinates of that point over there, I can write in terms of this line. So I can get the position vector of OM, and the position vector of OM is simply going to be 0 plus 2 lambda, 4 plus 0 lambda, and 1 plus lambda. That's the position vector of OM. And so I can work out the displacement vector PM. Or I don't actually want a PM, I want it to be MP. And that's going to be 6 minus the x component of OM, so that's 6 minus 2 lambda. It'll be 3 minus 4. And it'll be -1 minus 1 plus lambda. So if I join all of those together, I'm going to get 6 minus 2 lambda, -1, and lambda. That is my direction vector, MP. Hang on, there's something not right there. This last component's right. -1, -1, that's going to give me -2 minus lambda. Right, that looks a bit better. Right, what I have now, so I've got this vector, and I've got that vector. So in other words, I can go and take the dot product of 2, 0, 1, and dot product it with 6 minus 2 lambda, -1, and -2 minus lambda. And because those lines are supposed to be perpendicular, we know that dot product is going to equal 0. What do I have now? Well, I've got 12 minus 4 lambda. That's going to go, and I'm going to have -2 minus lambda equals 0. If I tidy all of that up, I'm going to get 10 minus 5 lambda equals 0, and so therefore lambda is going to equal 2. So now that I've got that lambda is equal to 2, I can go and put that back into OM. Remember, OM was the position vector, 2 lambda, 4, and 1 plus lambda. Okay, we've got it over here. So at lambda is equal to 2, well, then I'm going to have that OM is the position vector 4, 4, and 3. So how does this help me? Well, that means I've got my line over here. This is the point that I called M to start with. And this has the coordinates of 4, 4, and 3. And then we had P, which is a point over here that had the coordinates 6, 3, and -1. And if I want to find the length of MP, well, it's simply going to be the square root of 6 minus 4 squared plus 3 minus 4 squared plus -1 minus 3 squared. And that's going to give me the square root of 21. And if we take the square root of 21, we come up with, this is approximately 4.58 to 3 significant figures. And 4.58 was the same number that we had over there. So 2 different ways of approaching the problem, both equally valid. Hope that helps. You need to now go and work on some of these. Thank you. Goodbye.